We have locked the moon. There's a far side of the moon, there's a near side of the moon.
It has been over 50 years since our last moon mission. We have sent robotic spacecraft all throughout the solar system and discovered new planets during that time. Meanwhile, researchers are still trying to make sense of the rocky extraterrestrial visitor to our night sky. You may not be aware, but our lovely moon has two faces. If not, we are immediately informing you. We can only see one side, while the other is concealed from view. The intriguing part, though, is that these two sides or faces are completely distinct from one another. The explanation for this was the world's most well-known mystery, and it was never found. However, astrophysicists at NASA have now uncovered the answer to this riddle. However, this only scratches the surface. Recently, NASA revealed that they are also keeping an eye on a massive, rapidly growing anomaly on the moon. What possibly was that? Could the moon pose a threat to us here on Earth? Let's find out. Scientists reiterate that the moon still has many mysteries that need to be investigated as NASA gears up to send men to the moon once more by the year 2024, and amid conflicting messages from the US administration over the impending mission. Humans have spent countless ages gazing up at the moon, which is approximately 250,000 kilometers beyond Earth's atmosphere that supports life. Our ancestors perceived hazy shapes that reminded them of something familiar in its lamp-like countenance, and they concocted magical tales to explain these peculiar traits. But just 60 years ago, this timeless affection for our nearest celestial neighbor was forever altered when the Soviets' Luna 3 probe photographed the moon's previously unseen far side for the very first time. In Eastern traditions, a jade rabbit was imagined pounding the elixir of life, conjuring medicines, or mixing ingredients for rice cakes, while in the modern West, children are still lulled to sleep by the notion of a man in the moon. This other aspect of the moon, which is sometimes incorrectly called the dark side, a term for madness made popular by the music band Pink Floyd, results from its synchronous interaction with Earth. Imagine Buzz Aldrin and Neil Armstrong directing the Apollo 11 lunar module to the moon's surface after a 3-day voyage from Earth. The deep dark craters, the boulders dotting the alien landscape, and the fine dust that surrounds the spaceship as it ignites its descent engine for landing are all things they comment on as they get closer to their landing place in the Sea of Tranquility. However, when the lander touches down, Aldrin and Armstrong observe an oddity. The surrounding area seems to be rising, but hold on, the spaceship is actually sinking. As a stone dropped in quicksand, the 15-ton lunar module is being engulfed by the thick coating of moon dust. The two astronauts understand they won't be able to exit the spacecraft, but their overworked minds hardly register their dismay. They might never leave the moon if they can't figure out how to get the lander out of the way. While the Apollo program was taking shape in the early 1960s, the subject of whether the moon would swallow a lander was still up for discussion. Today, we know that the moon merely has a veneer of dust covering its essentially hard crust. The worry wasn't allayed until NASA sent a number of robotic missions to the moon's surface before the Great Leap of Humans. Although lunar research wasn't the main objective of the Apollo 11 mission, the 6 crewed missions that came after it and the robotic missions that came before it greatly increased our knowledge of the moon. Scientists were able to estimate the moon's age, composition, and formation thanks to the more than 2,000 moon rocks that the Apollo astronauts brought back. After the final person left the moon in 1972 and the last Soviet lander left shortly after, there were still fundamental problems that were unresolved for decades despite Apollo's significant scientific impact. The next time a robot touched the moon's surface was in 1993, when Japan's Haiten lunar probe was purposefully deorbited. However, a number of missions launched by NASA, China, India, and Japan in the late 2000s heralded the beginning of the second era of lunar exploration. In fact, over the previous 10 years, 14 missions from 4 different space organizations have successfully landed spacecraft on or near the moon. This includes China, which recently sent a rover to the moon's far side, marking a historic first. And there has never been a better time to be a fan with NASA getting ready to send humans to the south pole of the moon. For planetary scientists seeking to learn more about Earth's rocky neighbor, the increase in interest in lunar exploration is fantastic news. They are desperate to learn the answers to some pressing problems. Why, for instance, are moon rocks not as old as the moon? The moon is only around 60 million years younger than the solar system itself, at slightly over 4.5 billion years old. When the sun was still forming, the early solar system was chaotic and characterized by the frequent collision of solid objects as they swirled about it. This process, known as planetary accretion, led to the formation of progressively larger entities. The majority of the rocks the Apollo astronauts brought back were generated by impact events around 3.9 billion years ago, according to an analysis of the rocks they brought back, but nearly none of them were dated to the moon's first 600 million years of existence. This is strange, since you would expect to see a lot more rocks that were created from previous impacts when the planetary accretion process slowed down. As a result, researchers have proposed that the moon experienced frequent impacts around 3.9 billion years ago. This time period is referred to as the Late Heavy Bombardment, or more poetically, the lunar apocalypse. While this explanation satisfactorily explains the Apollo moon rocks, it also begs a significant question. What set off all of these rocks' assault on the moon? According to the dominant theory, the outer planets once orbited much closer to the sun and, as they migrated outward, sent large pebbles hurtling toward the moon. An opposing theory, however, contends that the deluge did not occur and that sampling bias is to blame for the overabundance of rocks with 3.9 billion year ages. Imbrium, Serenitatis, and Nectaris are the three most significant impact craters that have been sampled by the final 3 Apollo missions. It is critical to determine whether a period of intense bombardment had taken place, and new data suggests that the materials used to date the age of each of these craters may just be the leftovers from the impact that created the largest crater, Imbrium, about 3.9 billion years ago. The best method to resolve the lunar cataclysm controversy will be to travel to craters on the moon's far side or south pole, where samples are less likely to have been tainted by the Imbrium impact. The notion of the lunar cataclysm will be seriously called into question if the majority of those new samples are older than 3.9 billion years, and it will also provide scientists a better understanding of the circumstances in the early solar system. Where did lunar water come from is another question. Water was discovered inside rock samples brought back from the moon by the Apollo 15 mission, nearly 40 years after leaving the moon. The 2009 discovery, which raised the possibility that water may have existed on the moon since its formation, opened up a completely new field of study for the moon. NASA researchers used data from India's Chandrayaan-1 mission a few years ago to demonstrate unequivocally that water ice exists at the lunar poles. The majority of this ice is found near the South Pole's permanently shadowed craters, where the temperature never rises over -250 degrees Fahrenheit. This is fantastic news for upcoming lunar missions, which want to exploit this water ice for anything from rocket fuel to life support. The main concern for many scientists is how the water ice got there in the first place, regardless of whether it is there as large blocks or crystals mixed with lunar regolith. There are 3 basic hypotheses for how water first appeared on the moon, according to Paul Hayne, a planetary scientist at the University of Colorado Boulder. According to Hayne, the obvious idea holds that the water ice was deposited by encounters with asteroids and comets, where it melted and finally found its way to the poles. It's also likely that due to changes in surface temperature, ionized hydrogen from solar winds interacts with oxygen trapped in the regolith and finally escapes as vaporized water. Last but not least, it's conceivable that water existed in the material that initially created the moon and was pushed to the surface by volcanic eruptions. It's possible that all 3 processes were active, in which case it becomes unclear how much water was produced by each method. As a result, Hayne explains, we have some theories about how water got there, but the competing hypotheses have not really been tested yet. Nevertheless, there are some encouraging preliminary statistics. In order to strike the lunar surface at the South Pole, NASA launched the Lunar Crater Observation and Sensing Satellite in 2009. In addition to finding water, LCROSS also found a variety of other components that are typical of comets, indicating that at least some of the water may have traveled on asteroids. Hayne claims that it will be essential to send a robot or person to collect a sample and analyze its isotopic makeup in order to have a better understanding of how much of the moon's water was carried to the lunar surface by comets, asteroids, or solar winds. Really, that's the only way we can unambiguously link that information to a source. The subject of how lunar water ended up concentrated in the poles is still a controversial topic, according to Hain, even if researchers are able to pinpoint the origins of the liquid on the moon. The question of whether the water that is vaporized after comet and asteroid impacts can migrate over the surface of the moon, or if it gets stuck in the regolith, is currently dividing the lunar science community. Returning for additional testing is the only surefire method to find out. What lessons about the early solar system can we learn from the moon? Since the moon doesn't have much of an atmosphere and hasn't had volcanic activity in billions of years, its surface has remained largely constant. If only we could find out how to interpret them, says Prabal Saxena, a postdoctoral researcher at NASA's Goddard Flight Center. The craters are like the pages of a history book of the early solar system. As previously indicated, a popular explanation of the genesis of the moon postulates that our neighboring planet was hit by asteroids about 3.9 billion years ago. If the surface samples support the existence of a lunar cataclysm, this could also reveal a great deal about the formation of the solar system. It would imply that the Earth was battered as well as that the outer planets were once much closer to the Sun. Any water on the Earth's surface would have been destroyed as a result, eradicating any potential life. Unexpectedly, it seems that the moon has preserved early solar history. Recent research by Saxena and his colleagues suggests that during the first billion years of our Sun's existence, its rotation was probably 50% slower than that of similar newborn stars due to the chemistry of the lunar crust. While the moon and Earth share many of the same elements, the moon contains far less salt and potassium. Saxena and his colleagues used this evidence to run models that demonstrated how solar activity can either deposit or remove these minerals from the moon. They then factored in information on the correlation between solar flares and star rotation speeds. The calculations suggest that the Sun must have been revolving slowly to produce the potassium and sodium concentrations found on the moon today. This information about the early history of the Sun can also be used to explain how rapidly Venus lost its water, how rapidly Mars lost its atmosphere, and how it affected Earth's atmosphere. There will be more significant concerns to address when NASA and other space organizations establish the groundwork for a sustained human presence on the moon. Even while we have a greater understanding of the moon than many other places, there are still a lot of critically crucial questions that remain unresolved. It may sound cliché, but the moon really is a stepping stone to other planets, and that is entirely accurate. In a way, the moon serves as our solar system's equivalent of a Rosetta Stone. The greatest place to start is in our own backyard if we aspire to comprehend and perhaps travel to far more distant planets. On the other hand, one mystery that has only lately come to light concerns the finding that something enormous is hiding beneath the south pole of the moon, behind the South Pole Aitken SPA Basin, the largest impact crater ever created in the entire solar system. Although no one knows what it could be, it is undoubtedly large enough to alter the moon's mass's gravitational pull. The most prevalent hypotheses speculate that it is a piece of heavy metal from a projectile that struck the surface in the distant past. However, this is far from certain, and it's unclear what this mass is doing suspended underground. The heat should have caused it to move instead of being immobile like Han Solo and Carbonite, since we know the moon's interior is still somewhat active. But for now, all that scientists can tell with certainty is that the blob is enormous, perhaps weighing somewhere around 2.4 quadrillion US tons. Imagine burying a mass of metal 5 times the size of Hawaii's Big Island underground. Approximately that much unexpected bulk was found, and now we're gradually understanding why the two sides of the moon are so dissimilar. Imagine that it is 9:30 p.m., you've just gotten home from dinner and are getting ready to make a cup of chamomile tea for the evening. However, you take a moment to take a short look at the moon before sauntering inside. A bright orb with hazy, smooth black patterns on it looks back. It's shiny, brilliant, and most importantly, it's familiar. But from down here, you've only ever seen this side of the moon. The far side of the lunar surface is an entirely different side from the one we can see because it doesn't face Earth. It will never. With the help of the Soviet Luna 3 probe, humanity actually caught its first view of the secret zone in 1959, and it wasn't at all what we were used to. It lacked the distinctive deep gray patterns and was rough, covered in a ton of craters. Even later missions showed that it contained entirely different components. Our moon actually has two faces, and scientists are still attempting to explain why they are so dissimilar. However, a recent study may now have an answer for a key feature of this puzzling lunar dualism. It involves shadows, a significant impact that occurred many billions of years ago, and lava. In essence, the wavy hues we see on the moon are known as a lunar mare, and they are made up of ancient lava from the moon's surface volcanoes. It is somewhat odd that the far side of the moon lacks these traces, because if one side has a volcanic history, the other definitely should as well. A related question was posed by the research team for the new study. They examined what might have happened in the distant past, long before there was any volcanic activity on the surface of the moon, using computer simulations. More specifically, scientists recreated the enormous impact that, billions of years ago, altered the moon's surface and created the giant crater known as the South Pole Aitken (SPA) basin that we previously mentioned. We know that big impacts like the one that formed SPA would create a lot of heat, said Matt Jones, a planetary scientist at Brown University and the study's primary author. How that heat impacts the mechanics of the moon's interior is the key question. They discovered that this massive collision would have produced a plume of heat that transported a number of certain chemical components to the near side of the moon rather than the far side. We anticipate that this contributed to the melting of the mantle, which led to the lava flows visible on the surface. In other words, those factors likely contributed to a period of volcanism on the lunar surface visible from Earth, but they spared the other side. Surprisingly, this theory also fits with another enigmatic feature of the moon. Many areas on the near side are known to contain substances like potassium and phosphorus, as well as substances that produce heat, such as thorium and other rare Earth elements. These substances, collectively known as Procellarum creep terrain (PKT), are absent from the moon's far side. It's strange. These are the ingredients, however, that the authors of the new study discovered in their models to be stimulating volcanic activity on the near side of the moon, and as a result of the impact. The South Pole Aitken collision is one of the most important occurrences in lunar history, and how the Procellarum creep terrain developed is possibly the most important unanswered question in lunar science. These two ideas are combined in this piece, although as time passes, more evidence will be needed to support this notion. Whatever the case, perhaps the next time you find yourself admiring the moon's majesty, you'll also give its hidden and uneven far side some thought. Thanks for watching another episode of Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.